Okay, here we are. I'm still working on oscillators, and now we're at the complicated stuff. This is the driven damped oscillator. I tried to make a little video of this for you. Let's just see what it looks like. So you can't. It's hard to do it with an actual mass that's not hanging. You actually need two springs because most springs don't both compress and stretch. But there you are. And I don't think that's actually a damped because I put a little card there. But that's fine. You get the idea. We want to model that situation. Okay, so we're going to do a little bit of a review. So let's start back from the simple harmonic oscillator. This just has a mass on a spring with the restoring force is proportional to the position. We've already done this, I know, but that's fine. So the Newton's second law equation for this is just the single force negative kx, and that's mass times acceleration. Reminder, I am using x double dot for the second derivative of x with respect to time, because it's cool. Okay. So if you solve for x double dot, you get that. And if you set the angular frequency to k over m, you just make this value up. Then I have actually three ways I can write a solution to this. These all satisfy the differential equations. So I could say x is a combination of sine and cosine. And I put the initial conditions in for you there too. And I have a video about this. Reminder, I have a video playlist, a playlist of all my oscillator videos together. This is part of a series. So check that out if you want to see the rest of this. I could also write it as just a cosine with a phase shift, or I could write it as a sum of complex exponentials with complex exponents. All of those work. They're all satisfy the differential equations, and we can use them. They're mathematically the same, so it's no big deal. Okay. Now we have the damped harmonic oscillator. So here's the same harmonic oscillator, but now imagine that there's a drag force that's proportional to the velocity, which would be x dot. So B is the drag parameter. So it's in newtons per meter, newtons seconds per meter. So force divided by velocity. So that means my acceleration equation looks like this. If it's the same Newton's second law, it's divided by size by mass. I left that part out. When doing work with it like that, we want to get into another equation. And I've solved this, but it's solving the damped harmonic oscillator is part of solving the driven harmonic oscillator. So that's why I'm going over it again. So I can put it in this form, right? I can move the negative b over m x dot and the negative k over m x to the other side, and I get this. And then I can write this as 2 beta x dot plus omega naught squared x, where omega naught is the square root of k over m. That's the same thing we have for the undamped harmonic oscillator, right? So the same thing. And then I'm going to say beta is b over 2m. And then this is the part where you should say, what the heck? Why is there a 2 there? Why not just say beta is 2 over m? And aha, we'll find out in just a second. You don't have to do that, right? It's a trick that if you do know how to do that, it makes things easier for you later. But if you don't, it's not a big deal. It's the same thing. It just looks messier. Okay, so we have this equation, x double dot plus 2 beta x dot plus omega naught squared x equals 0. I could write that as not a dot notation. Second derivative with respect to x. Second derivative is like an operator. And then I have a first derivative as an operator. Let's call that operator capital D. It's the derivative with respect to time. So d squared would be the operator operating on itself, which is the second derivative with respect to time. So if I do that, I can write the differential equation like this. So I have the whole operator is d squared plus 2 beta d plus omega naught squared, all operated on x, is equal to 0. Well, if I can write it like that, it seems plausible that I would be able to factor that out. I have a d squared and a d term. I should be able to factor that into two terms that when they multiply those together, I get what I want. And if I could do that, then I would have two things, one of which has to be true. Either d minus r1, some constant operating on x is 0, which gives me the differential equation x dot equals r1x, which I could solve, right? Just so you know that if I operate d on x to get x dot, and then I have minus r1x moved to the other side. That's where that comes from. That's an easy differential equation. And the same thing, do it again with another constant. So I could be able to do it twice. So R1, X2. But then, and then my solution is just C1, the sum of those two, right? If one of them is the solution, both of them should be the solution. So C1, some constant I don't know, R1, which I actually don't know, e to the R1t plus C2 e to the R2t. Okay. So let's go back to this operator. I need to find the roots of that operator, d squared plus 2 beta d plus omega naught squared. So let's just say A is equal to 1, B is equal to 2 beta, and C is equal to omega naught squared, because that's a quadratic equation. I'm trying to find the root of a quadratic equation. Even though its operators are not variables, that's fine. It doesn't really matter. So I can use the quadratic equation. So R1 is going to be negative b plus or minus or plus. R1 will be negative b plus the square root b. R1 is negative b plus the square root of b squared minus 4ac over 2a. And then R2 would be negative b minus the square root of b squared over minus 4ac over 2a. Now if I put in a equals 1, b equals 2 beta, and c equals omega naught squared, I get that term right there. And notice something. There's a 4ac under the square root. And then because I put in 2 beta, I get 4 beta squared. I can factor out the 4 of that and take the square root, and I get 2. So did I put that in here? And then the 2's cancel. So then I get R1 is beta plus the square root of beta squared minus omega naught squared, and R2 is the square root of beta minus the square root of beta minus squared minus omega naught squared. And then that's why we put beta is b over 2m. If you didn't do that, you would still have a solution. It just would have a fraction in there, and no one wants a fraction. You don't have to have a fraction. So that's why we did that. Okay. So now we know R1, now we know R2. We don't know C1 and C2, but that's fine. This is the general solution. C1 and C2 can be determined from the initial conditions. So we have that solution. Now, depending on the value of beta, which depends on the drag coefficient, and omega naught, which depends on the spring constant, we can get different kinds of solutions. And the first is underdamped. So imagine that beta is less than omega naught squared. If that's the case, then beta squared minus omega naught squared is going to be a negative number. And so the square root of that's going to be imaginary. So I can fix that, and, well, not really fix it, but deal with that better. If I multiply beta squared minus omega naught squared by minus 1, then I can switch to the order and then factor out the minus 1, so I get I times the square root of omega squared minus beta squared. That should be omega naught, sorry. And that's a positive number. So I have I times a positive number, and I'm going to call that omega 1. I'm going to call that omega 1 just so I don't have to write omega naught squared minus beta squared. So that's omega 1. But that means that we have imaginary exponents. There, omega 1 is, yeah. But if you put in imaginary exponents, then you get this. So x of t is negative e to the negative beta t, a dampening term. C1 e to the I omega 1 t plus C2 e to the negative I omega 1 t. And you remember from our solution before, that is a solution to a simple harmonic oscillator with a dampening term in front of it. So I actually could write it like this. Some constant a, the dampening term e to the negative beta t, and then cosine omega 1 t plus phi. And omega 1 is not omega naught, right? They're different. Okay, so let's plot this. So here's my solution, and here's my plot. So this green curve is the oscillating point. That's part of the curve. That's just oscillating with the frequency omega 1. Easy. And then the dotted is the exponential decay term. So if I combine those two together, I get the whole solution, which is this dampening curve. That's that. Okay. Fun stuff. Okay, they also have critically damped. I said critical damped. Should be critically damped. This is the case where beta equals omega 0. And in that case, my exponentials are just 0. So I have C1 e to the 0 plus C2 e to the 0. Those are just constants. So it's just a decay term. Then I have overdamped, where beta is greater than omega naught. In this case, they're still positive exponential, so it's not an oscillation. But I actually have 3 terms that oscillate. Well, I have 2 terms that oscillate. I have the e to the negative beta t. The first term isn't actually growing exponential because it's positive with respect to t, and the other one's negative, but overall it still dampens out. Okay, and this is what it looks like. Here's just some parameters. The overdamped is the blue curve, and the critically damped is the other one that they just stopped. That's fine. Okay, now we are ready. So here's my oscillator. I have the restoring force from the spring. I have a drag force from the air or whatever it is. And then I have a time varying force that I'm pushing on it. I'm driving it. Okay, so if I write this as Newton's second law, I get this. Fx is negative kx, that's the spring force, minus bx dot, that's the drag force, and then some driving term, f of t, and that's mass times acceleration. Now, it turns out that I'm obviously going to divide it by the mass. You know we're going to divide by the mass, right? Because I want to get it in terms of k over m and b over 2m. So let's define lowercase f of t as the force per mass, and it just makes things easier. Again, you could think of that as a trick if you want. It doesn't really matter. So now I have this is my differential equation. Now, I mean, the important thing to notice is that the only difference between this and the damped harmonic oscillator is that instead of being equal to 0, it's ft. That's it. And so I actually could write this as the same operator, d squared plus 2 beta d plus omega naught squared, and that's going to be equal to a linear combination of 2 terms, 0, which we already have, and ft. And so this is it's a linear operator, so that we can do this. So this is the trick. So there's my operator. That's wrong. That should just be d. Wrong. That's wrong. Okay, I'm not gonna fix it because I've already gone too far. I can't go back now. There's no going back. Okay. So it turns out that we can get the solution to this equation, and this is tricky. Okay, all this math. You think the math is kind of tricky. It gets even trickier, but it isn't. We need to work through this. We can work through it together. Okay, we can watch this video more than once. Trust me, I've watched this video more than once. I said that in the middle of the video. That's kind of weird. So x, the solution to the function is a solution to two solutions added together. XC is what we're going to call the characteristic solution. Some people would call it the homogeneous solution. It's the solution for the case where the force as a function of time, f of t, is 0, the 0 part, right? Which you already did. That's the damped oscillator. And then we need to find a particular solution to this, and we can add those two together. And that might seem weird. It's like if you can find the particular, just find the particular and just be done with it. But there is, and so there's my characteristic equation. We already solved that, and it's just x. It's just that damped driven oscillator where omega 1 is omega minus squared minus beta squared square rooted. Okay. But the important thing, I'll tell you this, and I think I might have this on another slide later. The important thing is by doing this, we can have the initial conditions contained in the characteristic solution. And we don't have to worry about initial conditions for the particular solution. We only need one set of initial conditions. So that's kind of nice. Okay, so now we need to find the particular solution. In order to do this, we need some way to represent this varying force. It could be anything, repeating force, and there is a way to deal with that. But let's just do the simplest possible driving force, which is a oscillating driving force. It's just F0 cosine omega t. So you'll notice there's 3 omegas, right? I have omega naught, the angular frequency of an undamped oscillator. I have omega 1, the angular frequency of the damped oscillator. And this is omega, the driving force frequency. Okay, so that's a hard differential equation, but if I pretend that I could represent this driving force as an exponential, if I can represent the oscillating cosine function as f0 e to the I omega t, it might make it easier to find a solution. But e to the I omega t is a complex number. Okay, so I need to solve this problem as a complex solution. So let's switch variables. Let's switch to a complex variable version of this differential equation. So instead of having x, I'm going to have z. So z double dot plus 2 beta z dot plus omega naught squared z is that complex function f of t. And then I can say the solution is the real part of that. Okay, because the real part of f0 e to the I omega t is a cosine function, right? So I can do that. And why are we doing this? Because by writing it as a complex exponential, I have a chance of coming up with a solution. I have a chance of actually guessing a solution. And I am going to guess a solution. You could probably guess a solution. Let's just pick. Let's just guess. If I have taken the derivative twice, plus a derivative, plus a constant, and I get e to the I omega t, maybe it's something like e to the I omega t. So let's say z is some constant c, e to the I omega t. Would that work? I don't know what c is, but would it work? Okay, so let's take the first derivative. That's pretty easy. The derivative of c e to the I omega t is I c omega e to the I omega t. And then take the derivative again, and I get z double dot is, now I have an I times I, so I get a negative, and then I have c, and then I have another omega, so I have omega squared e to the I omega t. Okay, so now let's plug this solution into my differential equation. I have z double dot 2 beta z dot omega naught squared z, and then my other function. So I get this. I just took those derivatives and was putting them in. Now I do have that 2 beta, I do have the omega naught squared, I do have the f0 like that. Now, you'll see here that I have an e to the I omega t. Oh, here's another e to the I omega t. Oh, here's another e to the I omega t. And one more, so they all cancel. Yay. That's good. So now I just have this. Negative c omega squared plus I c omega 2 beta plus c omega 0 squared is f0, the amplitude of the driving force. Now I want to solve for c. Remember, that's what I need. I want to say what c would satisfy this equation. So I can factor out the c, it's in every term, and then I can divide both sides by the stuff in the parentheses, and I get c is f0 over the negative omega squared plus 2i omega beta plus omega naught squared. Now, that's a complex number on the bottom, so I have a real part and imaginary part. Let's group the real part together and group the imaginary part together. And so I have omega naught squared minus omega, that's my real part. And then I have the I omega 2 beta, that's my complex part. But now I still have a problem, right? Because I have a complex number on the bottom. I want to get it in the term of real plus imaginary, and that's not that. So I can get rid of the imaginary number on the bottom of this by multiplying the top and the bottom by the same thing. If I do that, I'm not changing it. And that's the complex conjugate of that bottom. So in replacing the I with the minus I, then I get this omega naught squared minus omega minus I omega 2 beta. And if I do that on the bottom, I just get omega naught squared minus omega squared quantity squared. And then I get the omega 2 beta, all that squared, which is omega squared 4 beta squared. And then on the top, I have an imaginary number. Okay. And so what I want, remember, x is the real part of z. And z is c I omega t, and so there I have c as a complex number. So we need to think about how to get deal with a complex number, c, and a complex exponent. That's our problem. Okay, so let's switch to the imaginary complex, the complex plane with the imaginary axis and a real axis. And so any point, any complex number, I can represent as a magnitude r from the origin to that point, and an angle, which I'm going to call theta. A lot of people would call this phi, but I already use phi, so I'm going to use theta. Okay. And then I want to show you that if I have a real number, a complex number, some x plus I y, we can write that as r e to the I theta. That's important. Okay, so here's my complex plane. Here's r, here's theta, here's x is the distance in the real axis, y is the distance in the imaginary axis. So if I look at this just like a normal trig problem, it is a normal trig problem. Okay, then x is the hypotenuse of that triangle, so it'd just be r cosine theta. Y would be the adjacent side, r sine theta. And then I can use the Euler identity, which I'm not deriving. It says e to the I theta is cosine theta plus I sine theta. I will make a video on this at some point. I want to do it soon, but I got a lot of videos to make. So then if I just say x plus iy, I get r cosine theta plus I r sine theta, factor out the I get r cosine theta plus I sine theta. Boom! R e to the I theta. That's it. Okay, so, but since we're dealing with a normal trig problem, I can get the magnitude of r using the Pythagorean theorem. It's just going to be the square root of x squared plus y squared. That's that. And then I can get the angle theta, because I can say tangent theta is y over x. And so, oops. So where am I going? Okay. Tangent. Okay, that's fine. Tangent theta. Okay, so now we just need to find r and theta. That's what we need to do. So here is my c. I'm going to factor out the non-imaginary part, right? So I have f0, and then I have that omega naught squared minus omega squared plus omega squared 4 beta, and then I have a real and an imaginary part. Let's go ahead and make a new substitution. Gamma. Gamma is a fun word to write. Gamma, that's capital gamma. Let's just call that 2 beta. It just makes it look a little bit nicer. Then I have f0 over omega naught squared minus omega minus gamma squared. And then I have omega naught squared minus omega minus I gamma. So that's my real, this is my complex number here. This is real, right? So I don't really need to worry about that. And that's in the form, this is in the form of x plus I y. So there's that's that. Okay, so now we need to solve for r, but let's just, I made a little extra picture. So here x is this term, and y is negative gamma, right? Because it's x plus I y. So I can solve for r, it's just x squared plus y squared, so it's going to be this squared plus this square rooted, so I get the square root of omega naught squared minus omega squared plus gamma squared. And then the tangent theta is just y over x, so it's negative gamma over omega naught squared minus omega. Now I don't want to take an inverse, I want that to be a positive number, so if I can factor out a negative sign here and then cancel with that, so this is going to be gamma over omega squared minus omega naught squared, so that the order of those flipped, and now I don't have to worry about the negative sign there, and then that gives me the inverse tangent of gamma over omega squared minus omega naught squared. That's my theta. This is important. It does depend on both the natural frequency of the spring and the driving force. So there's my r, that's very important, and there's my theta, very important. Okay, let's not put in theta because it just gets too messy, but we do want to put in r. So remember, we're talking about the real part of c I omega, and we've been working on the c part. We still have the e to the I omega. So if I put everything in, so this is this with the e to the I theta, that whole thing is my c, right? It's still a complex number. It's still complex because I got my r, but the complexity is in the e to the I theta. But right here, you notice I have this term is the same as this term squared. So this is gonna, I can cancel one of these. So this is like this term up here squared. So one of them is gonna cancel, and I get, what happened? I get this. So I get just, this becomes a square root and that term's gone. So now I have f0 over the square root of all that, and then I have e to the I theta times e to the I omega t. Since those are multiplied by each other, I can add the exponents, and I get e to the I omega t plus phi. And so now we're in a good spot, right? Because that's the real number, and I know how to deal with the real part of a exponential. So there's my same thing. Oh, I messed my parentheses right there. That's my fault. That's one of me. Take off a point. I'm sorry. I'm not going to fix it because, like I said, I'm in too far. So I have some amplitude. This is an oscillating term. This is just some constant amplitude. I mean, it's not really constant. It depends on omega, right? It's constant once you start the whole thing. And then I have cosine omega t plus theta. So that cosine omega t plus theta comes right. That's the real part of this. Okay, so there we go. That's my particular solution. So now I'll just have to add that to my characteristic solution to get the whole thing, and boom, that is it. We did it, right? Okay, but you're looking at that and like, I don't even know what's going on. The gamma, the omega squared, omega, what the heck? Theta? What's theta? What's theta and 5? This is just, okay, I get it because I'm there with you. So let's have a little cheat sheet here. So here we have AC, okay? AC is the amplitude for the characteristic solution, right? So it's for the damped oscillator, and that's why it's the characteristic solution. That value AC comes from the initial conditions. So what is x at t equals 0? What's the velocity at t equals 0? And then we have phi, and that also is part of the characteristic solution. Again, that comes from the initial conditions. Okay, then we have this beta term. Beta is b over 2m. B is the real drag coefficient, and m is the mass. And remember, we just put that in to make our differential equation a little bit easier. It's not, you don't actually have to do that. Omega naught squared is also depends on the physical parameters. And again, we put that in there just to make our differential equation easier. Omega 1 is for the this damp-driven oscillator. I'm assuming that it's under-damped and driven, not over-damped and driven. Okay, that's a different problem. And in that case, we have that beta, the square root of beta squared minus omega naught squared is imaginary, so we switched this, we made omega 1. So omega 1 is the frequency of the damped, undriven oscillator. Then we have F0. This is the driving amplitude, and it's the force per mass. It's the amplitude of the force for the driving force. And we assumed it was a trig function. We wrote it as a cosine function. Omega is the driving frequency, so we just picked that. Gamma, it's just a way to make things a little bit easier. It's just 2 omega beta. So we know what omega is. We know what beta is, right? And then theta is this thing that you have to calculate. So it's the inverse tangent of gamma over the square root of, not square root, omega squared minus omega naught squared. Remember, those are backwards because we had 2 negatives. But that's it. That's your cheat sheet right there. Let's go ahead and plot this. I'm not done. No. The bell doesn't dismiss you. I dismiss you. You're welcome to pause the video and come back or even leave. I'm just trying to be funny. Okay, so here's a plot of the solution. I did this in Python. So I actually have 3 things here. I have the characteristic solution in red. That's just a damped oscillator. And you'll see that it dies down and it's dead right there. XP is the particular solution. It's just an oscillating right there. And then the blue is the real solution. So you'll notice that at the early part, the dampening stuff takes precedence. But when that dies down, then it just becomes a normal oscillator. And I made this so that the frequencies were different. The driving frequency and the characteristic frequency are different. And we're going to look at resonance in another video. But not today. Now, another way to look at this is with phase space. Let me give you a quick review of phase space. Phase space is a plot of, see, the problem here is that if I let this go on forever, it's just really hard to see all the details. I don't really care about time. So if I plot position versus velocity, I can see the pattern. It stays over here, right? As long as it's in this maximum position and maximum velocity, it's going to stay in that graph right there. So this is an undamped, undriven oscillator. It starts at some position up here in phase space with initial x and initial velocity. And then x right here is positive, so the force is negative. That means the velocity is going to decrease. So it's going to actually, and then x dot is positive, so it's going to be moving away from the x equals 0 axis. So it's going to move this way. Okay, so it has to move clockwise. And that's just an undamped, undriven, just plain oscillator. I don't know why I added that in there right there. Okay, so that's what it would be. And here's what it looks like. We can actually animate this too, because if I know, I can make it an animated graph, which is not too hard to do in Python. But it's just oscillating around. This is your simple, basic, simple harmonic oscillator, velocity versus position. Now, what if I want to do the same thing for the damped driven oscillator? Because I do. So I have, this is my solution, characteristic solution plus my particular solution. That's my x. I can find x's at all my times. But I need to also find the velocity. So if x is xc plus xp, then the velocity is going to be the sum of the velocities too. I can take the derivative of each one of those terms, which you don't have to do this, but it just makes my equation writing a little bit easier. So if I take the derivative of xc, then notice up here I have a time term right there, so I'm going to get a negative beta, and then I'm going to get that same thing multiplied by all that stuff. And then I have to take the derivative of this, which is negative sine omega 1. I get omega 1, and then, oh, I left that off. I left off the e to the negative beta t, but I put it correctly in my equation. So there should be an e to the negative beta t in there too. Sorry, I'm making a lot of mistakes, right? But the mistakes are what gives the whole video character. So, and then if we do the same thing for xp, here's my solution right here. I'm going to take the derivative. I only have one time term. It's this. So I get negative sine, and then I get an omega t. So that's that. And then I add these two together, and that's my total velocity. Now, here's what it looks like if I have no driving force. Just so I can do that by putting f0 as 0. So this solution just goes to 0. It doesn't matter what omega is. And here's what that looks like. It just eventually stops. Stops would be, it has to stop at the origin, right? Because if it's not at the origin, there'll be a force on it, because there'll be a restoring force. And if it's stopped, it has 0 velocity. So if it couldn't stop anywhere else. It has to stop at the phase space origin, but it just spirals in like that. And I think that's kind of cool. Okay, now what if I add that dampening force in? I get this. Sorry. And I ran a little bit faster because I ran it longer. And you'll notice that it eventually decays down into this simple harmonic oscillator, even though it's much smaller, just because of the initial conditions I picked. Now, here is something really interesting about phase space diagrams, is that in this case, it can cross its path, right? One of the things we say is you can't cross your path, but you can. If I had just a non-time dependent term and I'm at this point where they cross right there, then it'd be like, which way does it go? It wouldn't know. But the thing is, it does know, because when it does cross, time is different, so the driving force is different, so it can cross its path. Okay, that's that. Okay, we have one more thing to do here. And I want to show you one more way to solve this problem, and that's with the numerical calculation. I'm going to go over this quick because I've already made this video like way longer than I normally do. So let's just think about this. So here's my Newton's second law equation. I have the drag force, I have the restoring force, I have some driving force, and that's mass times acceleration. And then I can solve this for the acceleration, just divide everything by mass, and then that ft, capital FT, comes to ft. Now, what I want to do is to break the motion into small time intervals. In this case, I'm going to pick 0.001 seconds. And if I have a small time interval, I can assume during that time interval, I can assume this x double dot is a constant value, which it is not, but I can assume it is. Okay. If it is constant, I can write the acceleration as the change in velocity with respect to time. Delta x dot delta t. And so I can write it like this, and then I can use that to solve for x2, which is the velocity at the end of the time interval. x1 is the velocity at the beginning of the time interval. So there's my update velocity equation. I can do the exact same thing for x. I can assume x dot's constant and solve for the position at the end of the time interval. Notice right here I have x2, here I just have x double dot. That's because I can get x double dot by solving this equation, which is just an equation. And then I just found x2 dot, so I'm going to use x2 dot for the velocity. And then I can update the position. And then I just repeat all that. I just go to the next time interval, I recalculate x double dot, I find the new x dot, I use that to find the new x. And since x dot and x are changing, x double dot changes. So it's a complicated thing, but I'm cheating by breaking a small time interval. Amazingly, this works. So this is my program in Python as part of the program. So this up here, I'm just defining my function for the driving force. And then right here in line 26, I'm calculating the acceleration. That's x double dot. I wrote it as a. And that's just the same thing, negative kx over m minus bv over m plus f of t. That's it. And then I update the velocity. I just calculated that acceleration, so I'm updating. This is an update equation because in Python, the equal sign is an assigned variable. It says make it equal to, so it's not an algebraic thing. The v's don't cancel. And then I update the position, and then I plot it, and I update time. And you see, I get the same thing. Now, which way is better? Numerical or analytical? The analytical gives you the solution without having to put in numbers. I have to put in numbers here. I have to have a numerical value for mass. I have to have a numerical value for k. I can't get an expression for it. But you can see it's actually pretty easy to come up with this. I didn't have to go through 16 slides of equations to get that. So that's good. The other way is more accurate. I can have large time step because I'm not actually using the time step to, all I'm doing is plotting it. Here I have to have a small time interval or otherwise I'll have an error. So I think there's a lot to say about both solutions. This is the nice thing about this solution is that I think an introductory physics student, first year calculus-based student could theoretically do a damp-driven oscillator, whereas the other stuff's more an advanced undergraduate level. But that's that. Okay, so like I said, if you're still here, why are you still here? Don't you have better things to do? I don't know. I'm still here. The playlist, a link to the playlist is down below if you want to see the other oscillators. I definitely want to make a video about resonance, changing the parameters to see when you get the maximum final amplitude. But we're pretty close to being finished. So I'm not sure that I will do. There's also, you could use the same oscillator for chaos. But I'm just not sure what I want to do. So I definitely want to do the resonance, and hopefully I'll do that, and it'll be in this playlist too. But other than that, I'm pretty much near the end, so that's it.